Hello, everyone. So in this lecture, we're going to continue talking about steady heat conduction, or more specifically, thermal resistance concept and its application. We already talked about the application of thermal resistance in plane wall and composite wall, and how we can use it to estimate the insulation effects on enclosing as an application. Here we want to work on cylindrical coordinates. So typically when we have a long channel and pipe, cylindrical pipe and tubes, the heat loss is in radial direction, through the wall. And that's why you see insulation on the wall of the cylindrical pipes. So the temperatures typically changes in radial direction, not in axial direction. I mean, we have loss of thermal energy in axial direction also, but typically is insignificant compared to radial loss of thermal energy, because we have more temperature gradient. So in this case, we assume that temperature is not changing in this axial direction, not in this direction. It's supposed to be a straight line, and not in angular direction, and only in radial direction is changing. Okay. So this situation as mentioned in here is approximated in practice in long cylindrical pipes and spherical containers. Why long? Because when we have a very long cylindrical pipes, there is no end effects. So we can focus on the radial position only. So in this section, we just want to focus on the radial change of temperature. So let's say you have a cylindrical pipe or insulation with inner radius of r sub 1 and outer radius of r sub 2. If we get back to the initial definition of the thermal resistance concept based heat transfer rate, this is what we have. The temperature difference divided by thermal resistance, that gives me heat transfer rate in watt. In cylindrical coordinate system, if we perform the analysis, a steady state analysis, what we get for thermal resistance is this formula. So the derivation is a little bit more complicated than the derivation of the thermal resistance for plane wall. And I didn't put the derivation in here, but you are encouraged to look at that process and procedure in the book. So this is the thermal resistance formula for cylindrical wall. Natural log of outer radius divided by inner radius in the numerator, and in the denominator we have 2 pi, length of the pipe times thermal conductivity of the wall materials. So what does that mean? It means if you increase the outer radius, basically if you have thicker wall, then your thermal resistance is going to be larger because you're increasing R sub 2. And if you decrease the thickness, or when you decrease R sub 2, your thermal resistance is smaller, and that makes sense. By having a thinner layer of the insulation material, you are getting less resistance, less insulation between inside of the pipe and outside of the pipe. This is a general formula for cylindrical wall. For a spherical shell also, we have an expression for thermal resistance, conduction thermal resistance. So by the way, again, this is about conduction thermal resistance. What about convection? You remember that in plane wall, what we had was convection resistance at the fluid side. So here, if you have fluid, then there is thermal resistance and convection thermal resistance. If you have fluid outside, again, there is another thermal resistance, convection thermal resistance. So convection, conduction because of this wall, and convection. The same for a spherical shell. Convection inside, conduction through the wall of the insulation, and convection outside. So if you look at the general form of thermal resistance concept and use the steady state heat conduction equations, we can derive this equation. This is the equation that gives us the thermal resistance of a spherical shell with inner radius of R sub 1 and outer radius of R sub 2. So outer radius minus inner radius divided by 4 pi outer radius times inner radius times outer radius times thermal conductivity. Thermal conductivity. And this is, by the way, times, not minus. Okay, so this is the expression that we have for a spherical shell. Now, what is the thermal resistance demonstration of that concept? We have, as I said, for a spherical shell and for a cylindrical shell, a resistance, conduction resistance as a result of this layer of solid material or any other substance that is imposing resistance against conduction inside of the spherical shell or cylindrical shell. We have, if we have fluid, then we have convection thermal resistance. Outside, if we have another fluid, we have another convection thermal resistance. The inner temperature of the pipe or the spherical shell is T sub 1, outer surface temperature T sub 2, inner fluid T infinity 1, outer fluid T infinity 2. So if we want to thermal resistance concept between the inner fluid and the outside fluid, we use this equation. T infinity 1 minus T infinity 2, temperature difference between divided by total thermal resistance. What is the total thermal resistance? The resistance, the convection thermal resistance, because the fluid inside, the conduction thermal resistance, because of this insulation, and convection thermal resistance, because of the outside fluid. So this is what we have for cylindrical insulation or cylindrical layer of a solid material. Then for the fluid inside, also we have convection thermal resistance, 1 over HA. What is my area? If you have cylindrical wall, your area of convection for the inside fluid is 2 pi r times length of the pipe. For the fluid outside is 2 pi r sub 2 times length of the pipe times H2. So 1 over HA. Now, if you have a spherical layer and a spherical shell, then what we have again as a total thermal resistance is convection inside, a spherical shell, conduction thermal resistance, and convection thermal resistance. For a spherical shell, we have this formula according to the previous slide. For convection thermal resistance inside of the spherical shell, we have 1 over H of the fluid inside times the area, interior or inner area. What is inner surface area? 4 pi r sub 1 squared. Outer surface area, 4 pi r sub 2 squared times H2. So this is for cylindrical pipe. This is for a spherical shell. Now, again, if you have composite wall, they can be considered as a series of thermal resistances connected with each other. Okay. So if you have cylindrical composite wall, then you have convection for the inside, 1 over H sub 1 A1, or 2 pi r sub 1 times length of the pipe times H1. The cylindrical thermal resistance for the first layer, cylindrical thermal resistance for the second layer, third layer, and the convection thermal resistance for the fluid outside. Okay, convection thermal resistance, conduction, 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 and convection. And this is going to be your heat transfer rate equation. The temperature difference between 2 points that you choose. So you can choose T infinity 1 and T infinity 2. And in the denominator, you put this expression as your total thermal resistance to calculate your heat transfer rate. Or the same way that we had for plain composite wall, what we have for heat transfer rate is the temperature difference between any points divided by total thermal resistances between those 2 points. So here, instead of T infinity 1 and T infinity 2, if I choose T infinity 1 and T2, then I put the temperature difference in the numerator, and in the denominator, I have thermal resistances in between these 2 nodes only. So I have these convection thermal resistance and conduction thermal resistance for the first layer. Or if I choose T sub 2 and T infinity 2 nodes, in the numerator, I have temperature difference between those 2 nodes. And node 2 and node infinity 2. And in the denominator, I have all the thermal temperature, all the thermal resistances in between. The thermal resistance between 40, this is for the, by the way, this is for a spherical shell, I am sorry, the second one. Now, this is for cylindrical and 2 layers. I think this thermal resistance, yeah. So this thermal resistance shape is missing one resistance, because here in between, according to this, so it's better to use this one. Between T2 and T infinity 2, I have this thermal resistance, this thermal resistance, and this. I have 3. This is not the correct one. It's missing one thermal resistance. Okay, so this is for cylindrical wall. This is for a spherical shell. Now, what's the application? As I mentioned at the beginning of this lecture, this could be considered as a thermal resistance of insulation. One of the main applications is defining the appropriate insulation for a cylindrical pipe in industry. So we may think that as we add more layers of insulation, we are protecting the fluid inside from losing thermal resistance, or fluid inside the pipe from gaining heat from outside. But it may not be always the case. This is what we want to investigate in the next example. We want to see if by increasing the thermal insulation of a cylindrical pipe, we are always decreasing heat loss and energy transfer between inside and outside the pipe or not. In cylindrical pipe shell, the additional insulation obviously increases the conduction resistance of the insulation layer, because we are adding more layers. So the thickness is increasing. So outer radius is going to increase while keeping the inner radius constant. But what about the convection? Why? Because convection at the surface, at the outer surface, is a function of outer surface area. When you're adding more layers of insulation, you're increasing the outer radius. When you're increasing the outer radius, so let's look at this equation. When you are increasing the outer radius, you are increasing this value in the denominator of the resistance corresponding to convection outside by adding extra layers of insulation. So this increases, that means the whole term for convection outside decreases. So you are decreasing the thermal resistance, convection thermal resistance outside, by adding extra layers to the cylindrical pipe. It means you are increasing the heat transfer in the form of convection outside. But also at the same time, we are adding extra layers, so this term increases. So in the next example, we're going to see if there is any point where by increasing the thermal resistance of the conduction, we can get less heat transfer from inside to outside or not. So the question is there any optimum radius of insulation for a cylindrical pipe with a certain radius? This is the schematic of the problem. We have insulation, we have inner radius r sub I, a thin layer of metal substance, and this r is the radius of the insulation, outer radius of the insulation. So r sub I is the inner radius of insulation and outer radius of the metal pipe. You cannot change, so for certain situations, for any certain situation, you cannot change the pipe radius. What you can change is the radius and thickness of the insulation. So R sub I is constant, and that's why when drawing, plotting the thermal resistance circuit, I just start from the inner radius of the thermal insulator, because I cannot change anything before this T sub I point here. Here everything is constant, the radius, the thickness. So I want to work on this part, from this point forward. T sub I, another node at the surface of the insulator, and one point in the fluid. So this is the thermal resistance that I want to work with. To find if there is any optimum thermal resistance or insulator thickness, I need to write the heat transfer rate equation for this thermal resistance circuit. The temperature between inner radius and outside fluid divided by total thermal resistances that we have in between I and infinity. This one, conduction thermal resistance and convection thermal resistance. Conduction is natural log of R over R sub I, 2 pi Lk plus 1 over H 2 pi RL. R sub I is constant again, because R sub I is the radius or outer radius of the pipe. We cannot change the thickness of the pipe. We can change the thickness of the insulator. So R sub I is constant. Now we want to see how we can, if there is any certain radius that corresponds to minimum loss of heat from inside to outside, or basically maximum value of thermal resistance, total thermal resistance. So what we're going to do is maximizing these terms. We want to maximize this summation. To find the maximum or any radius corresponding to that maximum value, we need to calculate the the derivative of this total thermal resistance, right? This is my total thermal resistance, conduction thermal resistance, convection thermal resistance. And if I want to see if there is a radius corresponding to maximum thermal resistance or maximum R sub total, I need to find the derivative of this expression with respect to R and set it equal to 0. This is a derivative of this expression, total thermal resistance. And if I set it equal to 0, the R would be equal to K over H, conductivity over convection transfer coefficient. And obviously it has a unit of meter because K is watt per meter Kelvin and H is watt per meter square Kelvin. So this is the R that corresponds to dr over d lower letter r equal to 0. So this makes the derivative equal to 0. But does that necessarily means that this r gives me optimum total resistance? Does that really give me the best insulation, the maximum insulation, or not? So for that reason, I need to calculate the second derivative of total resistance for this specific R. So first I calculate the second derivative for this expression. Then I calculate this second derivative at this specific R that I just derived, the R that makes the first derivative equal to 0. If I calculate the second derivative, or just plug this value into this equation, this is what I get. This is a positive value, 2 pi k cubed over h squared. K and h are a positive value. They are heat transfer coefficient, convection and conduction. This is positive. What does that mean? At this point, at this radius, my second derivative is positive. It means this corresponds to minimum thermal resistance. This corresponds to minimum thermal resistance, or basically maximum heat transfer rate. Maximum heat transfer rate. So if I draw R, my R would be something like this. Oh, let me redraw it. Different color. Okay, so let's say this is the minimum point. So something like that. This is the R, just qualitative R plot. Because at this point, R equal K, for this specific value of insulation thickness, your second derivative is larger than 0, is positive. So your R is minimum at this point. Because second derivative is positive. It means your heat transfer at this point is maximum. That means you have to avoid this value. This is the thermal insulator radius that gives you highest amount of heat loss from inside to outside. If the main purpose of this insulation is blocking heat loss from inside to outside, then you need to avoid this radius. So this is not the optimum radius. This is critical radius, CR. So what is the best radius? There is no best radius. If you're at the left-hand side, if your insulator thickness, let's say, is here, outer radius of the insulator, not the thickness. If the outer radius of your insulator is here, by adding extra layers, you are basically increasing heat loss until you reach this point. But from this point forward, as you add extra layers to the insulator, you are decreasing heat transfer that is good, or you are increasing the thermal resistance. So up to this point, so if you are at the left-hand side of this value, or you're in the plot, or your thermal thickness, the insulator radius is less than K over H, by adding extra layers, you are decreasing the overall thermal resistance and increasing the heat transfer rate. But if you pass this point, if you pass this critical radius by adding extra layer, you are increasing the thermal resistance and decreasing the loss. That is good. So that was about cylindrical coordinates. How about spherical coordinates? So also we may have a spherical vessel, and for a spherical vessel we may need a spherical vessel insulation. That's why I want to assign you guys a practice problem that is very similar to the one about cylindrical coordinates and cylindrical pipe, but it's concerned about the spherical shell. So what I'm going to ask you guys to do is derive the expression that would be appropriate for an insulated sphere. So find the radius, find the radius of the insulation that may give you minimum heat transfer rate or maximum heat transfer rate or critical radius. So find that radius in a similar way that we did for cylindrical pipe. I want you guys to do for a spherical shell and find the radius that may give you optimum heat transfer rate or optimum or minimum heat transfer rate and optimum thermal insulation, or it may give you critical radius. So you need to figure out at the end, after finding the expression for that radius, if that radius is optimum insulation radius or critical insulation radius. Does that correspond to maximum heat transfer rate or minimum heat transfer rate? And thank you guys.